In our last section, section 3.5 in chapter 3, we're going to talk about the idea of a steady state or some long-term predictions. And what's cool about this topic is we're going to put together two ideas we've already learned, Markov chains, and the new thing we've learned, eigenvalues and eigenvectors, and how eigenvalues and eigenvectors can help us interpret some things with Markov chains. So I want to take us back to an example that we looked at when we were first talking about Markov chains, and we had this matrix of transition probabilities where people were moving in between cities and suburbs, and where were they 1 year later. So for example, if you lived in a city, you had a 96% probability that the next year you would be in the city, and if you lived in the city, you had a 4% chance that the next year you would be in the suburb. Okay, so hopefully this jogs your memory a little bit. And we learned that when the population began like this was city and this was suburb, that just after 1 year, this was the new population of the city and this was the new population of the suburb. And then we predicted kind of far out, 2050, what the populations would be. And we can see that city is going down. It was at 82, 80, and then 52.6 million. I think these are in millions, yeah. And the suburbs were going up. 163, 164, and 192. Okay, so the question is, the thing I want you to think about is, if we go out even further, is it possible that the population of this city would actually go to 0? Or is there some number that it kind of settles on and stays at? So let's assume that we've got the same number of people from year to year. That's not very realistic, but we'll kind of simplify the problem in that way. That the actual number of people doesn't change. And actually people are still moving, back and forth between city and suburb. But does it ever occur that we reach some sort of steady state? So the question we want to ask is, looking at the trend of these populations of the city, this is definitely going down, and the trend of the population of the suburb. And we always keep this as our transition probability matrix. That stays fixed, as well as the actual number of people, even though people are moving back and forth. So the question we want to ask then is, what is the long-term prediction of this situation? And so you can think of all the possibilities. Population could be maybe, it's just wildly, city population is going up and down sporadically. That doesn't look very likely because it looks like it's trending downward and there's nothing that's going to stop that trend. Same with suburbs. We wouldn't really expect climbing and then falling and then climbing. It looks like it's trending upwards because of the probabilities that we have. So really there's only two possibilities if we believe that this is just going to keep trending down. Either it trends down till it's at 0, or it trends down until it's at some point where it stays fixed. And is that possible, that the city population will just settle on a number and the suburb population also, as it grows? I mean, it can't grow indefinitely, but would it just settle on a number? So a way to say this mathematically is, will it ever happen that I have some vector of the number of city dwellers and the number of suburb dwellers, and I multiply it by my probability transition matrix, and I would get the next year's distribution of city dwellers and suburban dwellers. And does it ever happen that when I multiply it by that probability matrix, that I actually get the same thing back again? Okay, this right here is an example of a steady state. When you take your distribution and multiply it by the transition matrix, and you get the same thing. Well, this steady state sure looks a lot like that eigenvalue equation that we've been talking about as well. That you have a matrix, and you're going to apply it to a vector, and you actually get the same vector back again, or some multiple of that vector. In this case, it is the same vector back again. So this is where we see Markov chains being helped out by eigenvalues and eigenvectors. But we need to define a few things, and then we'll just push on and go through this example. So be sure that you understand the significance of this equation, that usually we're going from year to year and these transitions and things are changing, but here we have some year X where we have some data, we hit it with the transition matrix and nothing changed. So this is a steady state. And if this equation is true, then that matrix X, or any matrix X that satisfies that, will be an eigenvector of P with eigenvalue 1. So I'll tell you that some Markov chains have this property and some don't. And we'll talk about how we can tell. Some don't. So there is a special type of transition matrix of Markov chains that will tip us off that we could, in fact, achieve this steady state. And so the idea that we need is this. The transition matrix P of a Markov chain is said to be regular if some power of P has only positive elements. So some power of P has only positive elements. And at first that sounds kind of weird because these transition matrices, well, they were probabilities. Didn't they always have positive elements? We can't really talk about a negative probability. And that's true. They were always these types of numbers. But it is, when it says only positive elements, there can be no zeros in here. So we did have some transition matrices that did have zeros in it. So it's fine if it has a zero in it, but at least at some point a power of P has to transform into only positive elements. And once it does that, then it'll always have positive elements. You can't come up with a zero after that point. So this is going to be sort of the marker for a Markov chain that can achieve a steady state. Okay, so let's make sure we're understanding what this term means. So let's think about this matrix here, P. It looks like it definitely is a stochastic matrix. It looks like a matrix that would show up in a Markov chain. And our question is this a regular matrix or a not regular matrix? Well, this guy's kind of looks fishy. I mean, we have a zero. So as it is right now, it doesn't have all positive elements, but that's not the test. The test is, does some power of this matrix have all positive elements? So we might take like the second power of this and see what we get. And it turns out if you square this matrix, you get 0.79, 0.7, 0.21, 0.3. Okay, bingo. This is a power of the original matrix and it has all positive elements. So this guy is definitely a regular Markov chain matrix. So we feel good about this and we know that this is a regular matrix. So next we look at this guy, another stochastic matrix. These all look like good probabilities. And we want to know, is this regular or not regular? So this guy here, we at least know the first power of the matrix doesn't have all positive elements. But let's look at like a squared, a cubed, and see if somewhere along the line we get a matrix that has all positive elements. Here's a squared, so we're not there yet because we still have an element that's not positive. And here's a cubed. We still have this guy kind of hanging around. And what we're going to find is however many powers we take, we're still going to have this column looking like this. So this element here will never be positive. So over time, we'll just see that it fails. And it's not a regular transition matrix. And so this, whatever this is representing, whatever situation this is representing, it will not lead to a steady state. Okay, so some wording that I just want to make sure we get all on the same page. If we say that that matrix is regular, then its associated Markov chain is also called regular. So the Markov chain is a regular Markov chain. So the theorem stated explicitly is if you have a regular Markov chain and you have this initial vector x naught and a transition matrix P, then all of those vectors x naught, x1, x2, they're going to converge to one vector. We'll call it x. So these are like the population of city versus suburb from year to year. The initial value, and then the first year out, the second year out. Here things are changing. You know, all of these guys are different. But eventually they're going to converge all to one vector, one steady state vector. So this very special vector, when you multiply it by the transition matrix, you just get itself back again. So after that point, from year to year, forever after, it's just staying in that steady state. And so this is an eigenvector of p, and its eigenvalue is 1. So that's sort of the first thing that falls out of having a regular Markov chain. And there's one other thing. When you take these higher and higher powers of your transition matrix, they all converge to a matrix Q. And the crazy thing about Q is the columns are all identical, and each one is actually the eigenvector of P. Okay, so now that we know this cool theorem, let's take what we know and apply it to, let's find the steady state of that city and suburb population example. Okay, so here we go. We're back to this example. And is P a regular matrix, transition matrix? Definitely. I mean, even from the get-go, we have all positive elements. We don't even have to look at powers of P. It's already sitting there for us. So it's a regular Markov chain. And this Markov chain is going to achieve a steady state. So at some point, these populations are going to totally just become in a steady state, and they're not going to change. These numbers will not change from year to year to year to year. They'll stay exactly the same. So let's find out what those numbers are. What is the steady state of this situation? So we have to think about how to find an eigenvalue of this guy, or an eigenvector. We already know the eigenvalue is 1. So this is the typical equation for eigenvectors and eigenvalues, but we know that this eigenvalue is 1. That's the whole idea of a steady state, is that it stays as it is. So we could write 1, or we could just leave it implied. And so this is the situation that we find ourselves in. We want to find the eigenvector that goes along with this equation. And we know how to find eigenvectors. So just like olden times, we're essentially trying to solve this equation here. So we have 0.96 minus 1. This guy will stay just what he is. This guy will stay just what he is. And then we have 0.99 minus 1. All of that times x1, x2 is going to equal the 0 vector, and we just want to solve for x1 and x2. So I've started doing the subtractions where I needed to. Let's see, negative 0.01. And I'm going to go ahead and tag this guy along on the end and solve it using reduced row echelon form. So we'll put this matrix through RREF, and the matrix that we get out is, and once this matrix goes through reduced row echelon form, this is the guy that we get out. So we can read off the solutions and find out what the eigenvector is. So x1 is going to equal 0.25 x2. So it looks like the vectors are going to look something like 1, 4. So anything of this form will be an eigenvector. So we can say the eigenspace is anything of this form. Now, we have to go back because we can't say that there's 1 person in the city and 4 people in the suburbs. Those are just proportions. We know that there's this many people altogether, this many millions of people. So if we add up 82 and 163, 82 plus 163 is going to equal 245 million people overall. And so what this tells us is that as time goes on, these are going to be the proportion of those 245 million people in the different spots. So that 1R in the city plus the 4R in the suburbs, that will equal our 245 million people. And so if 5R equals 245, then R equals 49. So the steady state will be 49 million people in the city, and then this number times 4 in the suburbs. So 49 times 4, let's see, million in the suburbs. So 49 times 4 sounds like 196 million. Okay, so this is the claim that once you get to this proportion, it's going to stay, these numbers are going to stay fixed. That doesn't mean that people aren't moving. People are certainly moving between the cities and the suburbs, but once you're at this point, if one person moves to the city from the suburbs, then someone has to move the other direction to make sure that these numbers stay the same. So the numbers are constant from that point on. It's not that the people are not moving, it's just that the numbers themselves stay constant. So I sort of want to convince myself that this is true. So I'm going to take this vector, this population vector, and run it through the simulation of this transition matrix and see if it really does happen that I get the same thing. So here's my transition matrix, and I'm going to take it and multiply it by this population distribution, 49, 196. And the claim is that I'm going to get 49, 196 after I multiply this. So let's make sure that happens. So I go ahead and do this multiplication on my calculator, and what I get is 49, 196. And of course I will get that forever after if I keep trying to multiply by this. So this truly is the steady state. There's one last question I want to ask before we go. What if our population had started with a different distribution? What if we'd had a lot more people in the city and few people in the suburbs? Would this have changed what the eventual steady state would have been? So my question is, what if we started out with 240 million people in the city and only 5 million in the suburb? Will that affect what the eventual steady state is? So will that change the steady state? So in the first year, this is what happens. That city population definitely goes down and the suburb population definitely goes up. What if we took something like p to the, p to the 8th? Let's see what happens after 8 years. Okay, after 8 years, the population looks something like this. 69.3. Definitely trending how we think it'll trend, but will it really ever get to here, or will it reach some other steady state? Let's take a look at maybe p to the 40 times that initial condition. And once I've gone 40 years out, this is what my population looks like. So now there's a lot more people in the suburbs and cities going down. Let's go out 90 years and see where we are once we started with this. Okay, I'm actually going to change this. 90 years, I just don't think it's going to move enough. Let's go way back. Let's go 250 years forward. And so, think of this is like similar to going back to Revolutionary War times, or, we're actually going forward in time. So many, many, many years in the future, what is the distribution going to look like? And when we do this multiplication, this is what happens to the distribution. We get 49.000, a little bit, and then 196. And we know that once we're there, we stay there. So this guy too, he, even though we started in a different initial value, we did end up at that steady state. And this is true of these regular Markov chains. It doesn't matter where you start. The probability matrix determines everything about the steady state. So even though we started with a ton of people in the city, we ended up at this steady state from this initial value that we started with. So steady states are independent of your initial value. So in a regular Markov chain, steady states don't care where you start. They don't care what the initial value was. They're just going to trend towards where they want to go, and they're going to stay there. So just finishing up this example, our transition matrix here, we are going to take higher and higher powers of it and see what matrix those powers tend toward. So these powers of the transition matrix are changing for sure. They're different, and they're tending towards this matrix, 0.2, 0.8. Remember that the columns will be identical, and they represent the eigenvector. Our eigenvector was 1, 4, and this is actually just a multiple of this, which is totally legal. It's still in the eigenspace, so we do get these eigenvectors of this situation, this regular Markov chain. So what these represent is, if you're just some random person, no matter where you start, you have a 20% probability of living in the city, and you have an 80% probability of the long-term probability of living in the suburbs. And it doesn't matter where you started. You could have started in the city or the suburbs. These are the probabilities of long-term where you'll be living. So what we've been able to see is these Markov chains are really enhanced with the knowledge that we've learned about eigenvalues and eigenvectors. And that's one of the really cool things about linear algebra. You know, you learn these new topics and you're able to piece things together and really supercharge the information that you do know with new information that it enables you to answer more questions. So this is awesome that we're tying a lot of topics in together here.